Hello. This is Matthew from Collegica. Today, I'm going to show you how you can design and implement a complex system, without hiring more people or spending more money. Sounds impossible? Well, it's not. In fact, some of the most successful and innovative systems in history were created by small teams with limited resources. How did they do it? And how can you do it too? Stay tuned and find out. Let's see how complex systems are designed. Model-based systems engineering, or MBSE, is a common practice in the aerospace and automotive industries. Here, we look at a simplified version of the V diagram. The design process in this diagram starts at the top left, where business requirements are defined. At this stage, high-level requirements coming from all the main stakeholders, including the involved companies, organizations, regulators, and markets, are documented. At the next stage, the requirements of a well-defined project with a limited scope is defined. The project has a start date, end date, and objectives that are deemed feasible within the given time and budget limit. The system level, or L2, is where the technical architecture design begins. Based on the project requirements, a set of technical requirements and a modular design with subsystems are defined. The next stage is to specify the requirements and design the architecture of each subsystem and their components. The last part of the definition and decomposition process is to define the requirements of each component. In all the previous steps, defining a requirement should be accompanied with defining a test procedure to verify if the requirement is satisfied. Usually, the requirements are defined in a general language that, against all attempts, are still open to interpretations. The tests, however, are defined in a deterministic and repeatable manner. After the requirements of the system, its subsystems and their components are defined, the components are implemented. In a software project, this would be writing the code to implement the components. The right side of the V diagram consists of running verification tests against the predefined requirements and integration steps. Each implemented component is tested to verify if it satisfies the corresponding requirements. The components of each subsystem are integrated to implement the subsystem. Then a similar process is executed for subsystems to build the system. Note that the right side of the diagram is called verification and validation. The verification part is a technical process and within the scope of the system. The validation steps involve the client to verify general requirements of the project and the mission to be accomplished. There is a lot of literature about model-based systems engineering. Here are some of the resources you can use to learn more about MBSE as it is used by organizations such as NASA. OpenMB is the most recent methodology to integrate MBSE into the technical design and implementation process. They have created an open-source collaborative system for engineers to work in the language of their choice, and document and share their results across other tools. So far, they have created model development kits for Jupyter, Mathematica, MATLAB, and Cameo Systems Modular. A modular system is a system that is composed of smaller and simpler components that can be reused, replaced, or reconfigured. In a modular system, all the components may get replaced over time, but the components interact, or the middleware keeps the system together. This helps to maintain the system over time. One of the main benefits of modularity is that multiple teams of engineers can work in parallel on the same complex product. As long as they keep the interfaces of each component to the rest of the system, they can make changes and integrate the resulting component back into the system. Some common examples of modular products are Lego bricks, where the customer can create different shapes and models. IKEA furniture that are made of different components with standard connections. And desktop computers made of different components to create different computer specifications or performance. There are different types of modularity. Modularity in use means that customers can customize or configure products according to their needs or preferences. Modularity in design means that designers can create different products by reusing or modifying existing modules, IKEA furniture. Modularity in production means that producers can manufacture different products by using common processes or resources. Reusability provides a lot of flexibility when it comes to software components. Software is becoming more and more important in shaping the way we use and enjoy our products. Whether it's a car, a phone, a smartwatch, or anything else that has some kind of digital component, software can make a big difference in how we experience them. In the past, the features of a product would remain the same if not declining during its lifetime. Software-defined products, on the other hand, can gain new features through over-the-air updates. They can also be personalized for each customer, because the main features are defined and implemented as software components. Open research is a movement that aims to make research more reproducible, transparent, reusable, collaborative, accountable, and accessible to everyone. It means that researchers share their work openly with other researchers and the public through digital tools. One way to understand open research is by looking at its definition by the Organization for Economic Cooperation and Development, OECD. They say that open research is the practice of making the primary outputs of publicly funded research results, publications and the research data, publicly accessible in a digital format with no or minimal restriction. But open research is not just about sharing publications and data. It also involves sharing other elements of the research process, such as methods, software, code, protocols, documentation, preprints, peer reviews and more. In general, research results are expected to be publicly available, reusable and transparent. Why is this important? Well, open research has many benefits for researchers and society. For example, it can increase the quality and reliability of research by allowing others to check and reproduce the results. It can foster collaboration and innovation by enabling researchers to build on each other's work across disciplines and borders. It can enhance the impact and visibility of research by reaching wider audiences and increasing citations. It can promote public trust and engagement with science by making research more transparent and accountable. Of course, open research also comes with some challenges and limitations. For instance, it may require more time and resources to prepare and share data properly. It may raise ethical or legal issues related to privacy or intellectual property rights. It may face technical or cultural barriers within institutions or disciplines that are not used to sharing their work openly. The Turing Way Handbook to Reproducible, Ethical and Collaborative Data Science is one of the most comprehensive resources for learning about open research. It includes guides to reproducible research, project design, communicating and ethical research. This handbook itself is the result of an open collaboration across a sizable community and published as open source software in a public repository on GitHub. Results of open research are published in many forms. Open data means documenting and sharing your research data openly for others to reuse. For example, you can upload your data to a public repository or platform that allows others to access and download it. Open source software means documenting your research code and routines, and making them freely accessible and available. For example, you can use an open source license for your code or software that allows others to modify and distribute it. Open hardware means documenting your designs, materials, and other relevant information related to your hardware, and making them freely accessible and available. For example, RepRap is a project that creates self-replicating 3D printers that can print their own parts. Open access means making all your published outputs freely accessible for maximum use and impact. You can find a comprehensive list of open access journals on Wikipedia. Open notebooks is an emerging practice that means documenting and sharing the experimental process of trial and error. For example, you can use a blog to share your notes, observations, hypotheses, partial results. Open scholarship is a broader term that extends open research further. It relates to making other aspects of scientific research open to the public. For example, open educational resources are educational materials such as textbooks, courses, videos, etc. that are publicly available to be reused and modified by anyone. For example, you can access and download free textbooks from OpenStax or free courses from edX. Equity, diversity, and inclusion are principles that ensure scholarship is open to anyone without barriers based on factors such as race, background, gender, and sexual orientation. Citizen science is the involvement of members of the public in scientific research activities such as data collection, analysis, or dissemination. For example, you can participate in citizen science projects such as Zooniverse or Foldit. By adopting open scholarship practices, you can enhance the quality and impact of your research, as well as engage with wider audiences and communities. You can also contribute to social justice and public good through your research. The FAIR Guiding Principles are a set of technical attributes published in 2016 to increase the findability, accessibility, interoperability, and reusability of data. To be findable, data are assigned a unique and persistent identifier, described with rich metadata, registered or indexed in a searchable resource, and linked to other data. To be accessible, data are retrievable by their identifier using a standard protocol that is open, free, and universally implementable. Metadata are accessible even when the data are no longer available. To be interoperable, data use an accessible and broadly applicable language for knowledge representation that can be integrated with other data, applications, or workflows. To be reusable, data have a clear and accessible data usage license, and follow domain-relevant community standards. Open source software is an important resource for innovation. It allows users to customize, modify, and improve their software according to their needs. It reduces costs, time, and resources for software development. It prevents vendor lock-in and promotes interoperability. It fosters innovation, collaboration, and learning among developers. Even if you are working alone on a project, stop renaming files and folders as an alternative to version control. This approach causes confusion as it lacks a single source of truth. A version control system, VCS, lets you track how a set of files changes over time. You can use a VCS to go back to previous versions of any file or the whole project easily. A VCS helps you collaborate with others on a project without interfering with their work on the same files. You can make branches with a VCS to try out different changes, such as new features or bug fixes, separately from the main branch. You can work on these branches alone or with others. Then you can merge back the changes you want to keep to the main branch. You can also save a specific version of your work as a tag or a release for later use. You can create Git repositories and decide who can see your repository, everyone or only you and your invitees. Using GitHub Pages, you can make a website with your files. If you have a domain, you can point it to your GitHub page and get a free and personalized website. With GitHub Actions, you get a free cloud computer. You can use it to run workflows automatically, such as testing, deploying, or publishing your code. GitHub Projects is a feature that allows you to create and manage projects within a GitHub repository. A project is a collection of items that can track issues, pull requests, notes, and custom fields. You can organize your project items on a Kanban-style board and create views for specific purposes. GitHub Projects helps you plan and prioritize your work effectively. With GitHub Discussions, community members can have conversations about the project, including asking and answering questions, sharing updates, discussing ideas, and following decisions. With GitHub Wiki, you can create and host documentation for your GitHub repository. Your repository's wiki lets you share long-form content about your project, such as its usage, design, or core principles. GitHub Wiki uses Git and supports features like version control, access control, bug tracking, task management, and continuous integration. When a team of developers work on shared repositories, they can face many challenges. If they don't have a plan or don't choose a proper naming convention for the branches, team members might get confused about where the latest version of certain features are. Another challenge is that if the dependencies or environment variables are not properly documented, a code that used to run with no issues might stop working. The worst is that nobody knows why it failed and how to fix it. If the team does not have a uniform and well-documented development environment, some features might work on one computer but nowhere else. If the team is not on the same page about what the requirements of the project are, they might make assumptions that are not correct or not compatible with other team members' assumptions. Also, even if the requirements are clear, developers might not be on the same page as in what order the features should be implemented. Defining the objectives and key results of each milestone of the project is of great importance. A binder, in the software project structure context, is a code repository that contains the source code and enough information to reproduce an environment to run the code for further development or for use in production. The binder also includes continuous integration and continuous deployment jobs that are automatically executed by GitHub Actions, for example, after a change is committed to the repository. Test-driven development, TDD, is a software development methodology that emphasizes writing automated tests before writing the actual code. The main benefits of TDD are: it improves the quality and reliability of the code by ensuring that it meets the requirements and specifications. It facilitates refactoring and maintenance by making the code easier to understand and modify. It encourages simple and modular design by focusing on small and testable units of functionality. It enhances collaboration and communication among developers and stakeholders by providing a common language and feedback mechanism. To apply TDD, developers follow a cycle of 3 steps. Write a test for a specific feature or functionality that does not exist yet. Run the test and see it fail, which indicates that the code does not meet the expectation. Write or modify the code to make the test pass, which means that the code satisfies the requirement. Now that the requirements are satisfied, review the code and refactor. This cycle is repeated until all the features or functionalities are implemented and tested. The tests serve as a documentation and verification of the code behavior. DevOps is a set of practices that aims to improve the collaboration and communication between software development and IT operations teams. DevOps also emphasizes the automation and integration of various processes such as testing, deployment, monitoring, and feedback. By adopting DevOps, organizations can deliver software products and services faster, more reliably, and with higher quality. Having said that, a key point about DevOps is that DevOps is not a specific tool but a set of multiple tools chosen based on the requirements of the teams in the organization. Using GitHub search function, you can use keywords, filters, operators, and qualifiers to refine your search. For example, you can search for repositories by language, topic, license, stars, forks, etc. You can also search for code snippets by file extension, path, file name, etc. You can also use advanced syntax, such as in name, in description, or in README to narrow down your results. Topics are labels that help you discover projects related to a specific subject or domain. You can browse topics by categories or explore trending topics on github.com/topics. For example, you can find projects related to machine learning, web development, or data science. The Explore page showcases curated collections of projects that are popular or interesting in various fields. You can browse collections by categories, such as featured topics, trending repositories, trending developers, recommended repositories based on your interests or activity history. You can also subscribe to newsletters or follow accounts that share updates on new or noteworthy projects. There are also many websites and tools that help you find software solutions on GitHub based on different criteria. For example, awesome lists are curated lists of awesome resources for various topics hosted on GitHub. You can find awesome lists for programming languages, frameworks, libraries, tools, books, podcasts, or courses by visiting github.com/syndraris/awesome. Code Triage is a website that helps you find open source projects that need your help. You can browse projects by language, popularity, difficulty level, number of issues, etc. You can also sign up to receive daily emails with issues that match your skills and interests. Libraries.io is a website that monitors over 3 million open source libraries across 37 different package managers. You can search for libraries by name, description, license, dependencies, or contributors. You can also discover new or updated libraries by subscribing to feeds or newsletters. Now that you have a solid understanding of complex systems design, open research, modularity, and development practices, it's time to put that knowledge into action. Choose a real-world problem or a topic that you're passionate about. It could be something in your field of interest or an everyday challenge that technology can help solve. Once you've chosen your topic, conduct thorough research to understand the problem space, investigate existing solutions, and identify the limitations that you can address. The goal here is to gather insights and requirements to guide your solution. Create a code repository on a platform like GitHub to start developing your project. Make sure to document everything clearly, including the source code, setup instructions, and any dependencies. A well-organized repository is essential for collaboration and future maintenance. When implementing your solution, follow the development practices we've discussed, such as modularity, test-driven development, and DevOps or MLOps, depending on the nature of your project. These practices will help ensure that your solution is robust and scalable. If possible, create a simulation environment to test and validate your solution. A simulation can provide valuable insights, allowing you to demonstrate how your solution performs in different scenarios. Finally, share your project as an open-source initiative. By making your work public, you not only contribute to the community but also invite collaboration, feedback, and further development. This is an opportunity to turn your idea into a collective effort for a greater impact. Remember, the journey may start small, but with the right mindset, you can tackle significant challenges and drive meaningful change. Take the first step, think big, and make a difference.